So today's video is on determining enthalpy. Just a reminder what enthalpy is. The enthalpy of a reaction is the amount of energy absorbed or released per mole of reaction. There's three ways that it can be found. The first way is experimentally. This is what we were talking about when we were finding the heat of reaction in the calorimetry portion of this unit. So experimentally, you use Q equals mc delta T to find your heat. So it's the heat divided by your moles of products that are formed. And that's how you experimentally find your heat of reaction. So really, remember the units are kilojoules per mole. So heat, kilojoules, divided by moles, kilojoules per mole. Another way is graphically, and the last way is mathematically. Graphically and mathematically is what this video is going to be focusing on. So just to quick reminders, when a reaction releases energy, it is called an exothermic reaction. And we get a graph of like this, if we were to graph potential energy versus the course of the reaction. That's what this reaction coordinate down here means, is that it's the course of the reaction. So we have our reactants here and our products here. Don't worry about this activated complex right now. We're not going to be talking about that until we hit kinetics. Okay, so in an exothermic reaction, heat leaves the system and enters the surroundings, which gives us a negative delta H. And the reactants have more potential, as you can see on the graph, the reactants have more potential energy than the products. So the energy, to calculate the energy that's released as heat, we take a line from the products, we draw that over, take a line from the reactants, we draw that over, and then we find the difference between the products and the reactants, and that energy that's released as heat is our delta H of reaction. So pretty simple. In contrast, reactions can also absorb energy. Those reactions are called endothermic reactions. And they absorb energy from the surroundings, and that energy enters the system. And in an endothermic reaction, products have more potential energy than reactants do. So this creates a graph that looks like this. Again, our reactants are down here, and our product is up here. And in this case, like we said, our products have more potential energy than our reactants do. So again, we extend the lines over, take the difference between our products and reactants, and that allows us to calculate the energy that's absorbed from the surroundings, which in this case is our delta H of reaction. And in this case, it is a positive number. Unlike before, it was actually a negative number. You can also determine enthalpy mathematically. There's two ways that you can do it. The first way is using something called Hess's law. The other way is using enthalpy of formation. So we're going to talk about Hess's law first, and then we'll talk more about enthalpy of formation after that. So Hess's law is based upon the premise that enthalpy is a state function. Just a reminder of what a state function is. It basically means that it does not matter if the reaction happens in many steps or a single step. It just matters that it happens. So this idea allows you to combine steps where we know the enthalpy of those steps to figure out the enthalpy of the overall reaction. So there's rules. The first rule is that the steps have to add together to make the overall reaction. If they don't add up to the overall reaction, then those steps cannot be used. The second rule is that if you reverse a reaction, you reverse the sign of the enthalpy. And if you multiply a step by a coefficient, you multiply the enthalpy of that step by the same coefficient. And when the steps add together, once you get them all to add together to make the overall reaction, you simply add the enthalpies of those steps to get the enthalpy of the overall reaction. So we're going to show you how this works in an example. So calculate the enthalpy of synthesis of diborane from its elements according to their equation. So this here is our overall reaction. These down here are all the steps that I was talking about. So what that means is these steps, we have all the delta H's. Our overall reaction is what we're determining the delta H of. So in this case, so for each step, first thing you need to do is find your important substance. The important substance is one that appears in only that step and the overall reaction. So if we look at our substances here, B2O3, it does not appear in our overall reaction. That makes it not an important substance. Oxygen, again, not in our overall reaction, not our important substance that we're focusing on. So the boron is what shows up in our overall reaction here, and it shows up in our steps. So then it does not show up boron by itself in any of the other steps. So that's our important substance. So what we're checking for is two things. The first thing is that that important substance is on the same side as it is in our overall reaction, as well as that the coefficient is the same. In this case, boron is on our reactant side. Boron in our overall reaction is also in our reactant side. Second thing to check is our coefficient. Here it has a coefficient of 2, here it has a coefficient of 2. That means that it's good to go. We don't have to change anything in our problem because everything matches up. So we move on to the next equation, the next step. B2H6 in this case is our important substance because, again, it's the only one that shows up in the overall reaction and none of the other steps. However, in this case, B2H6 is a reactant in this step, but it's a product in our overall reaction. So it doesn't match up. So we have to make B2H6 a product in our step. In order to do that, we reverse the reaction. So to reverse the reaction, you just write it in reverse. So 3H2O and the state of matter is important, so you do need to include that, plus B2O3 goes to 3O2 plus B2H6. Now, the rule said something about when you reverse a reaction, you have to reverse the sign of that as well. So we reverse this step, so we need to reverse the sign of this step. So the delta H of this step, as it is now written, because we did that, is equal to positive 2035 kilojoules. So now we're ready to move on to the next step. So we cross this guy out because we're completely done with it. We're not using it in that form anymore. So we cross that out. Okay, the next one is H2 plus 1/2 O2. So here our important substance is the H2 because again it's the one that doesn't change or is in our overall reaction and not in our other steps. So in this case, H2 is on the correct side. They're both on the reactant side, but the coefficient is not correct. So in order to get a 3 over here, we need to multiply this whole equation by 3. So that means when we rewrite it, we'll get 3H2 plus 3/2 O2 goes to 3H2O liquids. And because we multiplied that reaction by 3, we need to multiply this delta H by 3 as well. So that equals 3 times negative 286 kilojoules. Okay, and again, once we're done with that step, because we changed it, we cross it out. Now this last step is kind of funky, and this is where the difference between honors chem and AP chem comes in. We have stuff here that doesn't appear in our overall reaction. So we're going to start canceling stuff out to see how we manipulate this one, because this one is going to be used to cross out stuff that didn't otherwise cancel out. So let me change the pen color here. We'll change it to blue so we can see things canceling out in blue. Okay, so here we have a boron. Well, we don't see boron in any of our other equations, so boron stays where it is. Next one, B2O3. Let's do the B2O3. So B2O3 is here. It's also here. So our B2O3 cancels out here and here. So we're not going to worry about that. The coefficients are the same. Our B2H6, that doesn't cancel out. Our oxygens. Well, here we have 3 halves. That's 1.5 oxygens. We also have 1.5 oxygens on this reactant side. 1.5 plus 1.5 is 3. So that gives us 3 oxygens on our reactant side, and we have over here 3 oxygens on our product side. So the oxygens will all cancel out as well. Okay, and then that gives us, well, oh, we can't cancel out these waters because they're different states. So here it's a gas, here it's a liquid, so we can't cancel that out. So that's where this comes in here, this third step, this fourth step, sorry. So this last step has liquid water on the reactant side and gaseous water on the product side. That's the correct side because we need this water gas here to cancel out, so we need it on the opposite side. Which means, but then same with the liquid water here. So right now, in order to get it to cancel out, we need to multiply it by 3 because our coefficients don't match what we want to cancel out. So we're going to have to change it to change this to 3, so we multiply that by 3, so it becomes 3 H2O liquids go to 3 H2O gases. And again, our delta H, we need to multiply that by 3 because we multiplied the reaction by 3. So the delta H is equal to 3 times 44 kilojoules. Okay, so now we go back to finishing our canceling out. And when we do that, back to the blue here. And so here our H2O gas here cancels with this H2O gas, and our H2O liquid here cancels with this H2O liquid here. And what we find that we're left with, so in this reaction, we're left with this substance. No wait, we didn't cancel, but cross that guy out. We gotta cross that guy out. And in this step, we have this substance left, and in this one, we have this substance left. So what we have left is 2 boron solid plus 3 H2 goes to B2H6. And this matches our overall reaction, which means that we can add up the delta H's that we used from these 4 reactions, the way that they're written now, to get our delta H of the overall reaction. So our delta H is then going to equal -1273 kilojoules plus 2035 kilojoules plus 3 times -286 plus 3 times 44 kilojoules. And kilojoules should also be written up here. Okay, so when we punch that into a calculator, -1273 plus 2035 plus 3 times -286 plus 3 times 44, we get 36, get an overall of 36 kilojoules. So that is our delta H. And even though it doesn't say kilojoules per mole, it is kilojoules per mole. That's insinuated. So that means our delta H equals 36 kilojoules per mole. The next way of doing this, finding the standard enthalpy, is using standard enthalpy of formation. So standard enthalpy of formation is the change of enthalpy that accompanies the formation of 1 mole of a compound from its elements with all the substances in their standard states. So a couple things that are important, and it is important that you understand this definition because it has shown up on AP tests in the past, and if you don't understand the definition, you miss out on some really easy points. So the idea is that it's the 1 mole of a compound, okay, and that's from its elements. So the reactants are the elements, all their substances in their standard states. Standard states is 25 degrees Celsius, 1 atm of pressure, and 1 molar solutions. That's what standard states means. Okay, so if we were to write the reaction for the standard enthalpy of formation of water, the reaction, the elements that make up the water are H2 plus O2. So it would be H2 plus O2 forms water. But the water, when we would balance it normally, we would put a 2 in front of the H2 and a 2 in front of the water, giving us a balanced equation. But that can't be the case here because it's the formation of 1 mole of a compound. This 1 mole is extremely important. So to keep the coefficient here of 1, that's where we use our half. So it's half O2. Now this still balances, and we have the delta H of this reaction is equal to the standard enthalpy of formation of water. Okay, so the way you write the standard enthalpy of formation is it's represented by delta H F. This little degree sign just means that it's the standard states. That indicates standard states. And the little F means that it's formation, so it means that this reaction, the delta H of this reaction, is equal to the number that you end up looking up. Okay, so to find the delta H of a reaction, you use the delta H naught of the products minus the delta H naught of the reactants. These values here, you look up in Appendix 4 of your textbook. Okay, they're in the back of your textbook, and they're in a giant table. Okay, so we're going to use the standard enthalpies of formation listed in Appendix 4 to calculate the standard enthalpy change for the overall reaction that occurs when ammonia is burned in air to form nitrogen dioxide in water. So here's our reaction. Right, here's our reaction again, and we're going to look these values up in our book. But before we do that, we're going to do all of our math, most of our math, our equations, so that we can just plug things in at the end. Okay, so the delta H of the reaction is equal to the delta H of the products minus the delta H of our reactants. So we list out all of our products first. So our products are 6 H2O liquids plus 4 NO2 gases. And that's going to be minus our reactants because we subtract them here. So all of our reactants get put in parentheses. So we have 4 NH3 gases plus 7 O2 gases. And so if we look up H2O liquid in our appendix, find water liquid is negative 286 kilojoules per mole. So we're going to take 6 times that negative 286 kilojoules per mole plus 4 times nitrogen dioxide, which is 34 kilojoules per mole, minus 4 times NH3 gas, which is negative 46. 4 times negative 46 kilojoules per mole, plus 7 times oxygen, which is 0 kilojoules per mole. Okay. So when we take the 6 times negative 286 plus 4 times 34, we get negative 1580. So our reactants are negative 1580 kilojoules per mole. That's minus our products, so 4 times negative 46 is negative 184. So minus negative 184 kilojoules per mole. And so if we take the negative 1580 minus the negative 184, we get negative 1,396 kilojoules per mole. And then a lot of times, so this is our answer here, and a lot of times a follow-up question on the AP test is usually some sort of solution stoichiometry. So if I had 10 grams of oxygen, what energy would be released? If I had, and so then it's just some simple stoichiometry after that, using this negative 1396 kilojoules per mole as a conversion factor. And if you have any questions, please remember to ask them, write them down in your Cornell notes, and I will gladly answer them in class. Thank you very much, and I will see you guys tomorrow.